Hi, good morning, everybody. So I would just want to continue the lecture on data. So yesterday we talked about data representation, different kinds of data, and what are attributes and different kinds of attributes. We also talked about simple ways of summarizing data, right? The box plots and quartile plots, scatter plots, and so on. So visualizing low dimension data is very simple. There are not too many options. There are not too many difficulties also in visualizing them. But when you go to high dimensions, things get more complicated. So let us look at some examples of this kind, both low dimension, that is more than one dimension, and also higher dimensions. So, so 1D, I've looked at an example, interesting example yesterday, right? The example of spectrum, how using colors actually to represent the intensity, the energy or power at a given frequency is a innovative idea. And also using this kind of a plot where you can also indicate the black lines, right, where there is missing energy. It can be done very elegantly instead of actually showing a magnitude spectrum. So similarly here in the bottom you see an example of microarray data, which is a 2D visualization example. So if you go to 3D, then you get into virtual reality. So there things get very rich. So a lot of creative solutions are possible. So this is an example of virtual reality reconstruction of an insect. I guess it's a fly, right? Sorry, yeah. And so you can interact with it. You can move it around, rotate it, and things like that. So it's a good example of 3D visualization. So other ways of visualizing data in higher dimensions. Again, there's an extension of histogram. So histogram basically shows only one dimensional data, right? You divide the data into bins and show it as a histogram. But if you have more dimensions, what do you do? So here is this is an example with iris data. Iris data is a classic data. It's quite a small data set. But in the early days of pattern recognition, even this data set was quite a challenging thing. So people used to use this data extensively to try out various algorithms for classification. So iris data is data about flowers, about 5 different kinds of flowers, and there are 4 attributes. The attributes are petal length and petal width, and sepal length and sepal width. So there are 50 samples of each flower type. Actually, sorry, there are only 3 kinds of flowers, not 5. So 50 samples of each flower type. In this plot, they are showing histograms. Uh, since there are 4 attributes, you can draw a separate histogram for each of the attributes. So that's what you see in this plot. Okay, so sorry. Let me. So for each attribute, you can draw histograms. And in fact, for each attribute, for each class, that is each type of flower. So these are 3 kinds of flowers: Setosa, versicolor, and virginica. For each attribute, each flower type, or each class, you draw a separate histogram. So these are the 3 histograms correspond to 3 classes, and for the sepal length variable or attribute. Similarly, for sepal width here, petal length here, and petal width here. So now these are the plots on the diagonal boxes, because diagonal boxes is corresponding to each single attribute. Now, if you look at these off diagonal boxes, so each box is at a I and j location. Okay, so jth row and ith row and jth column. So I and j now correspond to 2 different attributes, because this is a kind of a 4x4 matrix. Actually, you are looking at only the lower triangular matrix of a 4x4 matrix. Right? So ijth location now indicates the ith versus jth attribute. So these are scatter plots of ith versus jth attribute. So here again, since there are 3 different subsets in the data, each corresponding to one type of flower, you can have 3 scatter plots, okay, between against the ith attribute and the jth attribute. So similarly, you have separate sets of scatter plots for each pair of attributes, I versus j. So this is how you can represent multidimensional data, again using a combination of histograms and so you're using here histograms right, and scatter plots. It's a pretty elaborate representation, but it gives some idea at a glance of how different data sets are related and how they're different and so on and so forth. So for example, if you look at this, you see that in this space, right, if you look at, so basically you're trying to classify or segregate the three flowers based on the attributes, right? Now sometimes two attributes might be very similar to two different classes or two different flowers, but some other attribute might distinguish the two flowers. So for example, in this case, if you plot, you look at this pair, that is sepal length versus sepal width, which is what this particular graph is about, this scatter plots are about. This set of data is very well distinguishable. So this corresponds to the setosa parameter attributes for sepal length and sepal width are quite distinct from the same parameters or same attributes for the other two flowers. So for the other two flowers, versicolor and virginica, they're about the same. They're all overlapping a lot. But for the first one, it's quite different. Right? But if you look at, let us say, this pair of parameters, okay, so where you are plotting sepal width and petal width, right? So all the three flowers are well distinguished. So this picture tells you in what sense these three classes are similar, in what sense they are different. Okay, so at one glance you can see all this. Now another such representation, a very innovative kind of representation, visualization, is what is called a Pareto histogram, or sometimes also called a Pareto chart. So what Pareto chart gives you is like the frequency of different causes of a given phenomenon. So for example, in this case, the phenomenon is late arrivals of employees to a company. Okay, what are the causes that lead to late arrival of employees to a given company, right? And then these causes are given certain frequencies. Okay, so and for example, how many times do they come late because of traffic problems? That is some 50, some 60% or something like that. Then how many times they come late because, or how many cases they come late because they have to take care of a child at home? That is next one. Then how many times they come late because of public transport constraints or disruptions, or because of weather, because there's overslept. I mean, even that is a cause, right? It's realistic cause, or some emergency, some accident, or something. They fell sick suddenly, it's whatever. Now, so there are many causes that lead to this phenomenon, this effect of late arrival. Each of these causes has different frequencies. Now you order these causes in the descending order of frequencies. So so that gives an idea of which is a more important cause, which is a less important cause. Right? And then you draw an accumulated plot. So you add them up, right, one by one, and draw this accumulated plot, which is the orange graph. Now, if you cut this graph at any given point, let us say 151. Okay, so this is 90% point, right? So if you go to this point, that means if you look at all the causes less than that or before that, that will take care of 90% of the causes, right? That produce this effect. So okay, so thing is, if I just want to take care of 70% causes, then I just go to this point, and then look at all the causes before that. So it's easy to diagnose a problem and then take some kind of effective action to prevent the problem, right? If you organize all your factors in some kind of a prioritized basis, right, which is what the Pareto histogram does. So again, scatter plots we have seen already. Now let us look at correlation. So when you draw a scatter plot, you want to understand how the two. So have a scatter plot, right, against two variables x and y, and it's a bunch of dots. Now I want to see if there's any relationship between those two dots, those dots and those two variables as indicated by the dots. So if I have something like this, then probably they are related. But if the dots are just all over the place, right? I mean, I cannot fit a line through this. So they're probably not unrelated. They're totally unrelated. So how do you find that out? So one way to do that is through what is called a correlation. So that is, if as x, then x increases, if y also increases systematically, then they must be correlated. So how do you capture that? So we're only looking at increase or decreases. We're not looking at absolute values. So you take the deviation of the xi samples from its mean value, that's x bar. So the deviation of yi, the samples of yi from its mean, the y bar. Like take dot product. So that will tell you whenever xi increases over, compared to x bar, is yi also higher than y bar relative to its own mean. Okay, so that means if that happens systematically, then this expression, this sum of products will tend to be high. Okay. In addition, if we also wanted to, factor out the scaling, aspect, that I don't care whether x's are much larger in magnitude in general than y, so the scale doesn't matter. But I just want to look at the trends. Is x increasing whenever y increasing? This is y is increasing. That's what I want to see. So in order to take care of the scale or factor out the scale aspect, right? We divide this by the standard deviation. Because standard deviation gives you some notion of the scale of the numbers or the spread of the numbers. So we divide this both by standard deviation of s, that is sx, and standard deviation of y, that is sy. And this summation, which is divided by n minus 1, you can also do n, because if n is a large number, then it doesn't matter. So standard deviation itself is given by this square root of sigma xi minus x bar whole square, and standard deviation other one is square root of sigma yi minus y bar whole square. So this whole thing is called correlation, also called Pearson correlation sometimes. Okay, so then let us look. We can also plot scatter plots in 3D. Anything more than 3D, obviously, it gets very messy, and you don't do that normally. Although there are ways of you can train yourself to understand four-dimensional data. I mean, it's just a whole hobby in itself. Beyond, there's a lot of websites and YouTube videos on that. Okay, so so if you can also plot 3D scatter plots like this, right, which gives some understanding of the data. Then let us look at visualizing spatiotemporal data. So this is an image plot, purely spatial data. So I have an image, and so there is an intensity. Now, these black lines that you see, right, it's called a contour plot. These are level curves of this image. So image, you can think of an image as a function, right, of x comma y. Let us say output is z. Right, now take values like z is equal to c. Okay, so z is equal to c, that means f of x comma y is equal to c. This will be a curve, and these are called level curves. We have talked about this in the context of method of Lagrangian multipliers. So if you take this curve, they take this surface f of x comma y and make it equal to c, then it's like cutting the surface using a horizontal plane, and that section gives you a curve. Sometimes a closed curve, sometimes an open curve. Now, this curve tells you where all the function has same value. Okay, so because sometimes the grayscale image or even the color image, because there's a color mapping between intensity and color here. The color bar tells you that. That may not give you a good intuition of the variations in the surface. But to give a more precise value, if you superimpose these level curves on this color map, right, it gives a better effect. And this is called a contour plot. The surface plot. I mean, same thing. You project or display the surface as a kind of a three-dimensional surface, right, or a 2D surface embedded in three-dimensional space. You can also plot vector fields because this is so when we talk about multi-dimensional, we mean multivariate functions. So f of x, x1, sorry, x2, etc. This is a multivariate function. But if you want to plot a vector function, right, that means y. So this is y is equal to f of x comma this thing, where x is in Rn n dimensional, but y is a scalar. Output is one dimensional. right? Only input is n-dimensional. So this is a scalar function. But what if we have a vector function? So I'll call this y equal to f of capital Y is equal to f of capital X, where x is in Rn and y could be in Rm. So y is also a higher dimensional vector. Okay, that's called a vector function. And how do you depict that? So obviously, if you go to high dimensions here also, there is the practical problems. But suppose you have a low dimensional vector field where, so this example is a situation where n is equal to 2 and m is also equal to 2. Okay, so that means at every point in this 2D space, there's a vector. So how do you depict such a function, such a vector function? So this is a vector field. So at every point, you just have to depict the vector as an arrow, small arrow. The length of the arrow gives you the intensity of the vector at the strength of the field at that point, and the direction of the arrow gives you the direction of the field. So very simple, right? And MATLAB, for example, allows you to make these kinds of plots. There is something called a quiver plot, right? Using which you can plot vector fields. And you can do the same thing in 3D. It's exactly the same thing, but so y equal to f of x, and x is in R3, y is also in R3. So at every point in this 3D space, I have a vector which is three-dimensional vector. Now you can even go to higher dimensions. So in higher dimension, there is no simple way, depending upon the problem, depending upon the type of data. People have come up with various innovative ways of depicting high dimensional data. Now, like I said, this is where things become more like an art than a science. So for example, here they are depicting the four-dimensional data of the iris data, 3 classes and 4 dimensions, right, using what is called a parallel coordinates plot. So what do they do here? They take each of these attributes, sepal length, sepal width, petal length, and petal width, plot it as, so take for example some flower and one of the setosa flowers, right, and its sepal length, let us say, is here. So I plot it as a dot, mark it as a dot here. Its sepal width is here, so I mark it here, okay, at some point. And if you plot it on this vertical line, its petal length is something else, so I plot it here. And its petal width is something else, so I plot it here. Now I connect these 4 dots like this by these 3 line segments. So this entire line segment now represents that vector of 4 attributes. It's a strange way of representing, but that is what is called parallel coordinates plot. So basically, the line when it is connected, all there are 4 different values which can be marked off on these 4 different y-axis. But when you have just 4 dots, you won't have the feeling that all the 4 dots belong to the same record or same vector. So therefore, you connect them by a line and make sure you color the line in some specific color, so that you can distinguish that class from some other class, right? And this line will be a piecewise linear curve, right? And so you will see bundles of these lines, and at a glance you can see where these lines are similar and where they are different. So for example, if you look at versicolor and virginica, they seem to be quite similar when it comes to sepal length, right, and sepal width, because the blues and the yellows overlap a lot, greens, whatever, the greens overlap a lot in terms of sepal length and sepal width. But when it goes to petal length, they're somewhat different. So to distinguish versicolor and virginica, so you basically need to look at only petal length. Other three attributes are not very discriminative, right? Whereas the when you look at the setosa flower, this is much different from the other two. Right, if you look at both petal length and petal width, and both of them nicely segregate and distinguish this flower from the other 2 flowers. So like that, you can intuitively get an idea of the differences among different vectors or classes using this plot. Another innovative way of depicting high dimensional data is star coordinates. So again, if you want to depict the same iris data using star coordinates, so in this case, we have depicted the attributes on parallel vertical lines. In this case, we are depicting it on radial lines. So there is an origin, okay, and since there are 4 dimensions, you divide the space, these degrees around the origin into 4 sectors, and you have 4 axes. Now, each of these axes represents one attribute. The first and the distance by which you go on the direction will be equal to or proportional to that attribute. So this is attribute 1, attribute 2, attribute 3, attribute 4. So these 4 vectors together represent that particular record of the vector. Only thing is, you connect the tips of the vectors and you get a polygon. Okay, it won't be a square or anything, it will be some random quadrilateral in this case. Right, this quadrilateral represents one data point, right, in the iris data. Similarly, for some other flower, you might find, I don't know, something like this. Right, so you kind of depict the flowers as some kind of diamonds, right, these quadrilaterals. Or if you have, for example, 6-dimensional data, okay, so 6-dimensional data, you have to divide this into a hexagon of sorts, all right. Okay, you'll have 6 points like that, and you have to connect all of them using hexagon. It's not regular hexagon, it's a random hexagon. And that hexagon now represents your data point in 6 dimensions. So this is called star coordinates because each of them is, at the core of it, there is some kind of a star. Another funny and quite...
Hello, sir.
Yeah, go ahead. Hello. Hello. Yeah, please go ahead, ask the question.
Like, I need one more.
Hello. I can't hear you.
Sure. Can you go to previous slide? Like,
Yeah.
so like, how do we get this line? This is the last point for that particular axis, right? Like, we draw.
Yeah, let us say you have 4 attributes, right?
I don't.
You have 4 numbers.
Yeah.
A1, A2, A3, A4. Right? You have 4 numbers. Now, from the origin,
Okay.
so there are 4 attributes, so you only take 4 directions, and 4 directions must be uniformly spaced. Okay, like so each the angle between the directions will be 90 degrees. Right? This
Okay.
form
Like, this is for one data, right? Like, for
no, yeah.
one condition.
For each one data point which has 4 numbers, you will get one quadrilateral.
Okay.
So
But
if you
like,
want
how do we then train the model? Like, for training purpose, like, we use multiple data, right?
no, this is not training. This is only display, visualization. All these methods I am showing right now in this whole class is just how to display data in interesting ways, in interesting, creative ways to just to convey to the viewer what is the data like, how are the classes different, how are they similar, in which attributes are they similar, which attributes are they different, just to give an intuitive feeling. This has nothing to do with training
Okay.
at all. This whole class is about visualization.
Yeah, I get that point, but like, I was thinking like, we are trying to draw a particular shape using multiple uh, same class
Yeah,
of
so if
data.
you have
Okay, okay.
150, so for example, in this plot, all the 150 points are drawn here. One thing, it looks very messy. Right? The point of this graph is not to actually mark off the values. That's very hard. And that's not the need or purpose also. This is just to give an intuitive summary feeling of what the data is like. Right? If you want to do calculations, you go back to your numericals. This is just to draw some nice pictures, that's all. And this gets even worse. Look at this
Okay, sir.
example, Chernow's faces. So what this guy has done
Okay, sir.
is he suggested that you can display vectors as cartoon figures of faces. All right. So, for example, so any cartoon figure of a face will have like an oval shaped outline for the face and eyes, nose, and some mouth. Okay, so that's all. Now, so if you plot, if you map these various attributes, sorry, it looks very scary. Even I'm right. Okay, so if you map various attributes onto some properties of these features like nose length and mouth length and things like that, you will get faces which look different for different classes. That's what this guy has done. It looks funny. It looks quite silly, but it's interesting. So the sepal length is size of the face. That is height of the face. Sepal width is mapped onto forehead to jaw ratio. Petal length is shape of the forehead, and petal width is shape of the jaw. So based on that, if you draw these pictures, right, all the versicolor guys, they look like this. The Setosa guys are all very small, kind of compressed faces. The Versinica guys are very long faces, mostly, and so on and so forth. So this is funny. This is just more like time pass and entertainment. And you can even take it even further, right? So suppose you have so many different, like what here you have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 dimensions. Suppose you have 13 dimensional vectors, right? You are less than anything less than or equal 13 dimension. You can map each number onto one of these properties of the face and create these cartoon pictures of faces, right? And then see what it looks like. It looks crazy, but it's at least fun to do that. So people have explored very innovative ways of displaying data because it's not enough just to do calculations on data. You also want to have an idea intuitively of what the data is like. So similarly, multi-scale visualization. I think this text is very small here, unfortunately, in this figure. So basically, they are showing variation of some quantity, right, over a calendar year or actually a calendar month at 2 time scales. So one time scale is at the scale of days, another time scale at the scale of minutes, right? So thing is, look at this. This graph shows, let us say, black is high and light color is low, right? So immediately you can see that that value, let's say temperature, okay, the temperature is kind of mid-level, moderate on the first day, and second day it is even lesser, even lesser, even lesser, right? Again, temperature has gone up here, right? And then it's gone down again, gone down. Again by Sunday, Zontag, this Sunday, right? Again gone up and gone down, whatever, right? So this picture of this coloring scheme tells you how that quantity is varying from day to day over a month. The whole thing is a calendar month. Now you want to find the same thing at a much finer time scale of minutes. So what do? You divide each day, right, into multiple sections. Like, and this is, I think, it's probably, yeah, this is 1 hour. So each of these rows, right, I don't know if you can see my cursor, each of these rows is 1 hour. And you divide the whole hour into smaller sections of few minutes. Now, so that becomes a small band, small rectangular strip. So within that rectangular strip, you divide that into smaller strips. And for each strip, you give a color depending upon how much that quantity is at that time, or an average value within that small strip, within that interval of about 5-6 minutes. So now you see within each of these squares, so single square here represents 1 day. So if you look at the color variations within a square, you can see how the temperature or whatever it is varying within the course of during the course of a day, right? Now, if you look at both these pictures, if you put them next to each other, you can very nicely appreciate what is the gross variation at the scale of days over the entire month. That is what this first picture gives you. So this is at the scale of days. The second picture tells you what is the final variation. Yeah, at 5 minute, right? 5 minute blocks. So this is a scale of minutes. Both cover the same same interval of 1 month. So you can, so if you want to depict something like this, I can just give a graph I can just give a big graph, things going up and down for let's say 1 month. But that's not very creative. That's not very informative. It doesn't convey much, right? Whereas here, this guy has very cleverly packed it and structured this within like a calendar page, which is very innovative. And then use colors for each of these blocks. And then the second one is also put more variation within each of these squares. So all this is quite creative. This was described in some paper, Shima Bukuro et al. 2004. Okay, one more such example is what is called a circle segment display. It is similar to this star coordinates, right? It is just that you use some colors. So if you want to visualize data, you need to use a lot of color. You better make it beautiful, right? So in this case, for example, they're looking at 7-dimensional data. So for each dimension, so you divide this whole space of 360 degrees into 6 to 7 sectors. And for each sector, you take the value of the corresponding attribute, right? And then take those corresponding points. Okay, and so in this case, in the star case, the length is what indicates the magnitude of that attribute. Here it's not the length, but the color. Okay, so each, not the line, but each sector represents an attribute. And the color of the line, so in this case, this is attribute 1, and the color I give to that line indicates the value of that attribute. Okay, and an entire record is plotted at something is going on. Entire record is plotted at one distance from the origin. Okay, so you will have a regular polygon representing one record, a regular polygon of a given radius or given size, representing one record or one data point, which has 7 attributes, and the colors of various sites, right? That's what indicates the attribute values. So this is called a circle segment display. So other plots like circles, right? This is a very interesting plot. So this plot shows various cities and various airline connectivities among the cities. So thing is, you can. So the idea here is you plot the cities on the circumference of the circle. You locate the cities on the circumference of the circle, and then the connection is taken through the center. So thing is, usually when you have a bunch of nodes and their connections, if the number of nodes is n, right, number of connections or edges will be of the order of n square. So this is typical. If every node is connected to every other node, number of edges will be of order of n square. So therefore, you need to, when you are visualizing the connectivity among some n nodes, you need to make sure that you give enough area, right, to the edges part, because edges take much more space. Nodes only take space of n, edges take space of n square. Now, if you plot them like this on the world map, it looks busy. But if you plot them like this on a circle, right, the edges or the connections go to the core of the circle, which is of the area pi r square, right? And the cities are located on the circumference, which is of the dimension like 2 pi r. The magnitude is 2 pi r. So this n and n square kind of relationship is also achieved here in this depiction. Another thing is, when two cities have lots of connections, they actually place close to each other on the circumference, so that you don't take too much space inside the circle. Only when they have fewer connections, you have you put the cities far away. So that you make optimal use of the space inside the circle. So this is a very intelligent plot. This is called a circles. This is again similarly dimensional stacking. So here again they're showing 4-dimensional data. So the data has, let us say, x, y, u, and w. So 4 components. Now this xy, normally if you want to show x and y, you can have a graph, but how do you do u and w? So imagine that you have a kind of a graph, but with 2 scales. And there is a graph and within that you have the bigger squares indicate the XY positions. Within each of these squares, there is again a smaller graph which indicates UW positions. Okay, so you are able to depict 4 dimensions using this kind of a double graph, a graph within a graph. Then there is something called cone trees. The cone trees are good at depicting hierarchical data. Hierarchical data means, right, let's say the organizational chart of a company or an organization, or let's say IIT organization. At the top point, you have the director, right? And below that, you have a bunch of deans. Okay. Let's say below that, you have the departments. And this, here you have HODs. And below that, you have faculty. Okay, it's not that hierarchical. The IIT is more or less flat, but anyway, so this gives an idea, right? So you depict the organizational chart as a tree structure, right? Where there's a node at the top who is the boss of the whole organization, and then there is a tree structure. So you can depict this organization as a tree structure, but it gets very busy, right? It's very hard to pack information at the lower levels. So you won't have much space because you get too many branches at lower levels. So what do? People said, let us plot it as a cone tree, so you can make use of 3 dimensions. So from every node to its child nodes, instead of drawing it like this as a flat structure, but if you do that, then the child nodes, if there are too many child nodes, you won't have much space to depict them. Instead of that, you make it like a cone instead of a triangle. Okay, so in the cone, there are branches in the back and there are branches in the front. So all the leaf nodes will form like a circle, right? So that's what it is. That's what you see here. But obviously there is a problem with cones because I cannot see what is behind, right? Behind the hidden face of the cone. How can I see it? So for that, it's very simple. I mean, you can the program will let you interact with the image, and I can rotate it, and I'll just spin it, and then I can see what is hidden will become visible. Okay, but the depiction is there. So at every level, instead of having a triangle like this, right, I'll have a cone. So it is a tree of cones, right? So therefore, it's called a cone tree, and it's good for depicting hierarchical data, like organizational charts. One more advantage of a cone tree is when I have like a very busy cone like this, right? I can, let us say this guy is like some employee working in some workshop or something, and this is the director at the very top. What is the connection? So this guy has to make some appeal, right? Just to go all the way to the director. So obviously it will go through what is famously called the proper authorities, no, proper channels, right? You might have heard of this bureaucratic term called proper channels. What is the proper channel? This guy will talk to his immediate boss. That guy will talk to his section head, or that guy will talk to the workshop in charge. That guy will talk to, and it might come under a mechanical department. And so he'll talk to the mechanical HOD. Mechanical HOD will talk to, I don't know. It's very tiring. Okay, so you go through the entire path and follow the proper channel and go to the very top. So when you have a tree structure depicted like this, you can see clearly what is that proper channel, what is that pathway connecting the lowest nodes in this tree to the, let's say, apex. Right. Okay. So that's it. These are some examples of some sophisticated ways of data visualization. So now I said in the last class that we'll watch a very nice video by this statistician called Hans Rosling. So for that, I guess what I will do is, this is a TED Talk. I'll share the tab instead of showing the screen. I'll share the tab. So let me know if there's any problem. So can you hear it? Can you see it?
About 10 years ago, I took
Yes, sir.
Yeah, okay. So let me go to full screen.
on the task to teach global development to Swedish undergraduate students. That was after having spent about 20 years together with African institutions studying hunger in Africa. So I was sort of expected to know a little about the world. And I started in our medical university, Karolinska Institute, an undergraduate course called Global Health. But when you get that opportunity, you get a little nervous. I thought these students coming to us actually have the highest grade you can get in Swedish college system. So I thought maybe they know everything I'm going to teach them about. So I did a pre-test when they came. And one of the questions from which I learned a lot was this one: which country has the highest child mortality of these 5 pairs? And I put them together so that in each pair of country, one has twice the child mortality of the other. And this means that it's much bigger the difference than the uncertainty of the data. I won't put you at a test here, but it's Turkey, which is highest there, Poland, Russia, Pakistan, and South Africa. And these were the results of the Swedish students. I did it so I got a confidence interval, which was pretty narrow, and I got happy, of course. I had 1.8 right answer out of 5 possible. That means that there was a place for a professor of international health and for my course. But one late night, when I was compiling the report, I really realized my discovery. I have shown that Swedish top students know statistically significantly less about the world than the chimpanzees. Because the chimpanzee would score half right. If I gave them 2 bananas with Sri Lanka and Turkey, they would be right half of the cases. But the students are not there. The problem for me was not ignorance, it was preconceived ideas. I did also an unethical study of the professors of the Karolinska Institute that hands out the Nobel Prize in medicine, and they are on par with the chimpanzee there. So this is where I realized that there was really a need to communicate, because the data of what's happening in the world and the child health of every country is very well aware. So we did this software which displays it like this. Every bubble here is a country. This country over here is, this is China. This is India. The size of the bubble is the population. And on this axis here, I put fertility rate. Because my students, what they said when they looked upon the world, and I asked them, what do you really think about the world? Well, I first discovered that their textbook was Tintin mainly. And they said the world is still we and them. And we is Western world, and them is third world. And what do you mean with Western world? I said, well, that's long life in small family, and third world is short life in large family. So this is what I could display here. I put fertility rate here, number of children per woman, 1, 2, 3, 4, up to about 8 children per woman. We have very good data since 1960 about, on the size of families in all countries. The error margin is narrow. Here I put life expectancy at birth, from 30 years in some countries up to about 70 years. And 1962, there was really a group of countries here that was industrialized countries, and they had small families and long lives. And these were the developing countries. They had large families and they had relatively short lives. Now, what has happened since 1962? We want to see the change. Are the students right? It's still 2 types of countries? Or have these developing countries got smaller families and they live here? Or have they got longer lives and live up there? Let's see. We start the world. And this is all UN statistic that has been available. Here we go. Can you see there? It's China. They're moving against better health. They're improving there. All the green Latin American countries, they are moving towards smaller families. The yellow ones here are the Arabic countries, and they get larger families, but they longer lives, but not larger families. The Africans are the green down here. They still remain here. This is India. Indonesia is moving on pretty fast. And in the 80s here, you have Bangladesh still among the African countries there. But now Bangladesh, it's a miracle that happens in the 80s. The imams start to promote family planning, and they move up into that corner. And in 90s, we have the terrible HIV epidemic that takes down the life expectancy of the African countries, and all the rest of the world moves up into the corner where we have long lives and small family, and we have a completely new world. Let me make a comparison directly between United States of America and Vietnam. 1964. America had small families and long life. Vietnam had large families and short lives. And this is what happens. The data during the war indicate that even with all the death, there was an improvement of life expectancy. By the end of the year, the family planning started in Vietnam, and they went for smaller families, and the United States up there is getting for longer life, keeping family size, and in the 80s now, they give up communist planning and they go for market economy, and it moves faster even than social life. And today we have in Vietnam the same life expectancy and the same family size here in Vietnam 2003 as in United States 1974 by the end of the war. I think we all, if we don't look in the data, we underestimate the tremendous change in Asia, which was in social change before we saw the economical change. So let's move over to another way here in which we could display the distribution in the world of the income. This is the world distribution of income of people. $1, $10, or $100 per day. There's no gap between rich and poor any longer. This is a myth. There's a little hump here. But there are people all the way. And if we look where the income ends up, the income, this is 100% of world's annual income. And the richest 20%, they take out of that about 74%. And the poorest 20%, they take about 2%. And this shows that the concept developing countries is extremely doubtful. We sort of think about aid, like these people here giving aid to these people here. But in the middle, we have most of the world population, and they have now 24% of the income. We heard it in other forms. And who are these? Where are the different countries? I can show you Africa. This is Africa. 10% of world population, most in poverty. This is OECD, the rich country, the country club of the UN. And they are over here on this side, and quite an overlap between Africa and OECD. And this is Latin America. It has everything on this earth, from the poorest to the richest in Latin America. And on top of that, we can put East Europe, we can put East Asia, and we put South Asia. And how did it look like if we go back in time to about 1970? Then there was more of a hump. And we have most who lived in absolute poverty were Asians. The problem in the world was the poverty in Asia. And if I now let the world move forward, you will see that while population increase, there are hundreds of millions in Asia getting out of poverty, and some others get into poverty. And this is the pattern we have today. And the best projection from the World Bank is that this will happen. And we will not have a divided world. We will have most people in the middle. Of course, it's a logarithmic scale here. But our concept of economy is growth with percent. We look upon it as a possibility of percentage increase. If I change this and I take GDP per capita instead of family income, and I turn these individual data into regional data of gross domestic product, and I take the regions down here, the size of the bubble is still the population, and you have the OECD there, and you have sub-Saharan Africa there, and we take off the Arab states there, coming both from Africa and from Asia, and we put them separately, and we can expand this axis, and I can give it a new dimension here by adding the social values there, child survival. Now I have money on that axis, and I have the possibility of children to survive there. In some countries, 99.7% of children survive to 5 years of age, others only 70. And here it seems that there is a gap between OECD, Latin America, East Europe, East Asia, Arab states, South Asia, and Sub-Saharan Africa. The linearity is very strong between child survival and money. But let me split Sub-Saharan Africa. Health is there, and better health is up there. I can go here, and I can split Sub-Saharan Africa into its countries. And when it bursts, the size of each country bubble is the size of the population. Sierra Leone down there, Mauritius up there. Mauritius was the first country to get away with trade barriers, and they could sell their sugar, they could sell their textiles on equal terms as the people in Europe and North America. There's a huge difference between Africa, and Ghana is here in the middle. In Sierra Leone, humanitarian aid. Here in Uganda, development aid. Here, time to invest. There you can go for holiday. It's a tremendous variation within Africa, which we very often make that it's equal everything. I can split South Asia here. India is the big bubble in the middle, but huge difference between Afghanistan and Sri Lanka. And I can split Arab states. How are they? Same climate, same culture, same religion, huge difference. Even between neighbors. Yemen, civil war, United Arab Emirates money, which was quite equally and well used. Not.
Okay, I think let us stop there, all right, because I won't be able to finish the whole thing in this class because it's already 9:50. So let's continue tomorrow, and we'll also discuss what is nice about this video tomorrow. This is a very good example of a very innovative data visualization. Okay, so yeah, let's meet on Friday. See you. Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you. Good day. Have a good day.